Alright, example 8 is slightly different. It's got a uniform rod PQ hinged at a point P. It just means it's attached at point P. And it's held in an equilibrium at an angle of 50 degrees to the horizontal by a force of magnitude F, acting perpendicular. And it wants to know what value of F that is. What's going on? Well, if this pink pen is my rod, this is point P at the bottom here, so it's resting on the table, it's got a weight pulling it down, and why is it not falling? Because of my hand at the end here. So there my hand is representing force F. If I try and make it perpendicular, it's just about perpendicular, and that's stopping it falling. So the same options are available to us as were available in the previous question. You could resolve in an up or down. We've seen in the previous unit though it's better to resolve with or against the slope, but actually in this one we don't really need to resolve. Like if you did, you would try it and you'd find it's not much use. The only thing that might confuse you is if you resolved it without filling in any extra forces, because there is another force on this diagram that's not marked. If we go back to my pen, where's the other force that's acting on this pen? Right? The other force is at the table, because the pen is resting on the table, and we know that any object that rests on a table experiences a reaction force perpendicular to the table to stop it falling through. There is also a perpendicular reaction here. Right? So I could resolve vertically or horizontally, right, or diagonally, but actually it won't end up leading me to anything useful because I'm going to have two unknowns, R and F. But of course, like we said in the previous examples, the way to deal with extra unknowns like that is to take moments at one of those points, right? We don't want to deal with R, we just want to find out what F is. So if we treat P as the pivot, which actually it is a pivot, isn't it? Because we said it was hinged there, so it's attached there. Then we can take moments about it. So moments about P. And there's only two things, right? There's the force F, which is going to be, if we think about it turning from that point, it's going to be making it move in an anti-clockwise direction. So I'll use a little purple colour code for that. And we've got the blue one, which is making it move in a clockwise direction. So let's start off with the anti-clockwise, why not? So we've got we need the length, don't we? So what length have we got going on here? Well, it tells in the question it's length of 3 meters. So 3 meters is the length, so it's 3 meters away from that end. So it's 3 times F, so it's just 3F Newton meters in the anti-clockwise direction. Right? We don't need to do anything with angles because it's perpendicular. You can see the force is acting perpendicular. On the other hand, when we look at the weight, it's 8g because the mass is 8 kilograms, and it tells us that it's uniform, so it means we can assume the weight is the middle. Therefore, the distance, if the whole thing is 3, will be 1.5 because it's halfway. 1.5 times 8g, but here's where we've got to be very, very careful. Right, this is not acting perpendicular to the rod. So we have to think about the perpendicular directions of the rod, which I've put in an orange dotted line here. Now you've got a 50-degree angle here, so hopefully we're familiar from the other units that we've done so far in mechanics that this little angle in there, it's a bit small on the diagram, right, is going to be got by doing 180 minus 90 minus 50, which will give you a 40-degree angle there. I'll just colour it in to try and make it as clear as I can. Sorry, it's not the best, is it? So that's 40 degrees, the little orange one. So I've moved away from there, away from the 40 degrees to the perpendicular. So I'm going to have to multiply it by sine 40. Most common mistake on these ones definitely is people not remembering that if the rod's at a diagonal, it's perpendicular to the direction of the rod. So we have to think about resolving that angle in that perpendicular direction. So just work out what that is, 9.8 times sine 40. So this is 75.6 Newton meters, and it's clockwise. Again, it tells us it's held in equilibrium, means the clockwise and the anti-clockwise must balance. So we've got that 3F is equal to 75.6. So F is equal to 25.2 newtons in order for it to be held in equilibrium. Again, you don't use the R because it's at the point of pivot, so it has no effect on the turning. Or you could think of it as it's a distance of 0 from the pivot, so you'd end up with 0 Newton meters as well. Okay, that's example 8, and that's that lesson, the third lesson of moments. Here are the questions for you to do. Right, we've got question 1 and 2, just do the odd letters of those. Question 3 onwards, get progressively harder, but some really good exam style practice in there. I'll just make a point about tension, right? Some of the questions will also talk about a beam being suspended. So you can think of having a ceiling up here, right? And then these are ropes holding the beam, right? And they act in exactly the same as the reaction. So they'll have tension forces stopping whatever beam we've got. So if this is a beam, you can think of it as like lights hanging from the ceiling or whatever, right? They're holding on by the two tension forces, and this would be T1 and T2 in the same way that if we had the reaction forces, they would be from below. But the thing with strings is they're just holding you from above rather than supporting you from below. So there are a couple of questions in there about tension. It's exactly the same. Treat the strings like those little triangular supports and the reaction forces, and other than that, the questions will work mathematically exactly the same.